let's now figure out how to get these thermodynamic parameters using the steam tables. Well, actually, before I get ahead of myself, we could get the enthalpy values directly from the steam tables just by looking them up. But for the velocity, we can't find it directly from the steam tables. But what we need to do is we need to relate it to information we can get from the steam tables. Okay? And so, if you remember from even physics, general physics, when we talk about the velocity of something, it's going to be related to the mass flow rate. Okay? And that's because if we think about the mass flow rate, so let's think about mass flow rate 1. Based on our unit analysis, we could also say that's equal to some density times the volumetric flow rate. All right? We could further rewrite the volumetric flow rate as some sort of cross-sectional area times the velocity. So the cross-sectional area that the stream is flowing through, you can imagine it as a circle. So the area of a circle is pi diameter squared divided by 4. And then that area is going to be multiplied by a linear velocity. All right? And so from here, we could relate our linear velocity to the mass flow rate. In fact, we could rewrite this equation to solve explicitly for the velocity. Furthermore, we're dealing with a density here, but another way we could rewrite this, because we know that the inverse of density is the same thing as a specific volume, v hat. And so the velocity we could then rewrite like this, v1 hat. And this v1 hat, this is something that you can get from the steam table. Okay? All right. And so we did that for U1. We could do the same thing for U2. And if you go through that exercise, you will get this. Okay? All right, and so in order to solve for these velocities, that means we just need to look up the specific volumes of the steam at the inlet and the outlet. Okay? So just as a reminder, for the steam at the inlet, it's at 1 megapascal and 600 degrees Celsius. And the outlet, it's at 0.1 megapascals and 400 degrees Celsius. We're not explicitly told if we have superheated or saturated steam. And so the way we'll figure that out, if we jump to the steam tables in the book, is by looking up, if we go to the superheated vapor steam table in the back of our textbook, what we could do is we could just look up the pressure of the stream. So for the inlet, we're at 1 megapascal. And we see right next to it, there's a temperature listed, 179.91. That's the saturation temperature at that pressure. All right, and so in our case, the inlet's at 600 degrees Celsius, and so that means we're way above the boiling point temperature, and so that means our steam is superheated. Okay. Similarly, for the outlet, at a pressure of 0.1 megapascals, the boiling point temperature is 99.63, and so 400 is well above that. Okay, and so for both the inlet and the outlet, we're dealing with superheated steam. Okay, all right, and so now that we know we're dealing with superheated steam, what we need to do is we just need to look up the specific volumes. And just to orient you, in this superheated steam table, what we have listed is specific volume, internal energy, enthalpy, and this S variable, which is called entropy, which we'll talk about later in the course. In any case, the units for each of those things are actually listed here at the bottom of the table. So for specific volume, it's going to be in meters cubed per kilogram. And then for the enthalpy, which we'll need later, it's going to be in kilojoules per kilogram. Okay. In any case, let's look up the specific volume for the inlet. So the inlet's at 1 megapascal and 600 degrees Celsius. So that means the specific volume, if I can highlight it correctly, is 0.4011 meters cubed per kilogram. All right. And then for the inlet, it's 0.1 megapascals at 400 degrees Celsius. Oops. So that means the specific volume is 3.103. Okay? Now that we have that information, we could go back to our problem statement. Let's write those things down. V1 hat is equal to 0.4011 meters cubed. V2 is equal to 3.103 meters cubed per kilogram. Now that we have those specific volumes, we could just go to our equations, plug in, and get U1 and U2. And if we do that, we see that U1 is 127.7 meters per second, and U2 is 158.0 meters per second. Okay, so we see that the linear velocity actually speeds up as the steam goes into then out of the turbine. All right, so we got the velocities. The other things we need for our energy balance are the enthalpies. And that's going to be a little bit easier because we could just read those directly from the steam tables. Okay, so going back to the steam tables, for the inlet at 1 megapascal and 600 degrees Celsius, we get that, too much. We found the enthalpy there, so 3697.9 kilojoules per kilogram. And for the outlet, what we get is 3278.2. Okay. So let's write those down. Alright, so now we have basically everything we need to solve our energy balance. So let's go back to the energy balance equation 2. And we can rearrange it to solve explicitly for the shaft work. U2 squared. Okay? And then if we plug in everything, what we get is negative 1038.5 kilojoules per second. Alright. So now we solved for that work rate. The last thing I want to do, though, is I actually want to compare the contributions of the different parts of the energy balance towards the overall work rate. Okay. All right, and so the way I'm going to do that is first the mass flow rates M1 and M2 are the same, so that doesn't going to change. But what I want to do is I want to compare the differences between the kinetic energy change. So 1/2 u2 squared minus u1 squared. Right? And if we take those values and calculate, the number we get is 4.3 kilojoules per kilogram. Right? I want to compare that to the difference between H1 and H2. And that difference is 420 kilojoules per kilogram. Right? And so we see, if we compare the change in kinetic energy to the change in enthalpy, the change in kinetic energy is literally an order of magnitude smaller than that change in enthalpy. Right? So essentially, we see the kinetic energy change is essentially 1% contribution to the overall shaft work. All right? And so that's commonly, that's sort of what we see in thermal problems. And in fact, many times what you're going to do, depending on the problem statement, there are some cases where you do want to solve for a velocity. But in many cases, in thermal problems, we're going to ignore changes in kinetic or potential energy, because typically they're going to be much smaller compared to changes in internal energy, changes in enthalpy, or your heat and work terms. Okay? So this is in thermodynamics. We're typically going to make that assumption. That's the opposite of what you do in transport, where a lot of times you do care about the velocity or the change in potential energy. But in thermo, this is a typical assumption we're going to make.